the first thing we're looking at is this idea of KSP. You got your table there with KSPs. What we want to be able to do is write a balanced equation for the dissolution of a salt. That's what we were doing here in blue. All right? We've practiced that quite a bit with the soluble things back when we were studying chapter 4, actually. But now we're going to think about more with things that are considered insoluble. And then also predict the relative solubility of salts from their KSP values. That's something we can already do because you have that list. So if you look on the table, on that list that I passed out on the front of that sheet, let's look at all those values on there. And let's see who can find the very, very smallest number. And again, look at the scientific notation part to find out what's the smallest value on there. As soon as I turn off the lights, I'll tell you to read that fine print. Okay. So raise your hand if you think you found the smallest value on there. Let's see a really small one. Broadfoot, what do you see?
Mercury sulfide.
Yeah. Very good. I think that's the smallest one. Yeah, there's maybe a tie for that place also. The mercury 2 sulfide, 2 times 10 to the negative 53rd. And there's a few lines up, there's a tie for it with manganese 2 sulfide. Does anybody see anything smaller than 10 to the negative 53rd? I don't think I do either. So that represents the very, very, very least soluble, or the most insoluble compound on this whole table. So the smaller the KSP, the less and less soluble these things are, even though none of them are really soluble. So they're all terrible at dissolving. But among those, the worst at dissolving at all would be the smallest value. All right, let's go the other way. Again, they're all considered insoluble, so they're all like 99% or more insoluble. But maybe one of them is at least better at dissolving than anything else on this table. What do you see as the largest value on this table? What do you think, Alice? Mercury iodide. Good eye there, because it looks, I wonder if that's a typo or if that's really what's 1 point, I'll look that one up later. 1.1 times 10 to the negative 1.1. I'm going to look that one up. I mean, that for sure on this table, that's the largest value. That might be an error since it's a decimal place in there, but you're right, based on the numbers that they give us there, that would be it. What's another one that is relatively larger compared to the others on here? Probably see something that's 10 to the negative, something that's not super small. Silver sulfate. Silver sulfates. Nice. 1.5 times 10 to the negative fifth. Yeah, that one's going to be more soluble than pretty much anything else on here. There's another one around 10 to the negative fifth that I can, and there's a couple more around 10 to the negative fifth. Yeah, magnesium oxalate being 8.6 times 10 to the negative fifth. Calcium sulfate over there. Lost it. Yeah. I didn't lose it again. Yeah, 2.4 times 10 to the negative fifth. Good. So those that are around 10.4 times 10 to the negative fifth, something 10 to the negative fifth, still insoluble, but relatively more soluble than the others on the list. Everything on here, if you look up these on your solubility rules, they're all going to say these compounds are insoluble. Things that are soluble all have K values that are greater than 1. So those are things that are definitely going to dissolve quite a bit at room temperature. They'll have really large equilibrium constants. We only focus on KSP for things that are considered insoluble. One thing that insoluble compounds are related to are cave and cave formation, the way the stalactites and stalagmites form on there. That's a insoluble compound, calcium carbonate, COCO3. And that reaction is affected a little bit by temperature and by acid-base chemistry. So it actually changes the solubility depending on the temperature in the cave and also the acid-base properties of even the water in the cave. Hello, Mr. Patrice. Okay, I'll send her. Thank you. Bye. carbonate, and that changed to sulfate for some reason on there. Sulfate. Carbonate, which is insoluble. And with Le Chatelier's principle, this reaction can be driven forward or backwards depending on the temperature in the cave and also some of the attributes properties of the water that's seeping down through the ground. When the reaction is pushed this way, it's more likely to form those solid stalactites and stalagmites. When some of those properties are different, the reaction is driven more forward to dissolve a little bit of that calcium carbonate. And it ends up over, millions of years forming the whole cave system. Here's a definition of it for KSP, solubility product constant. It's this equilibrium constant. It describes a solid dissolving in the solution, and we reserve it for the solids that are considered to be insoluble. These values are going to be less than 1, and that reminds us that these are very much reactant favored. So the solid is what predominates. So far we've focused on all the examples we've looked at. It's always a 1-to-1 ratio for the product side because they have the same charge, whether they were both +1, or they're both +2 and -2. This was +1 and -1, I mean. So it was a 1-to-1 ratio. In a minute we're going to see what if there's a coefficient on there. That makes things a little more interesting. Does anybody need more time here? Okay. Anybody need more time now? Right. So this next one goes along with the example problem. It's just like we call it a pre-question that goes along with it. So first, we're going to be looking at CAF2 in this problem. So let's write the expression for the solubility product constant for CAF2, and then we're going to look up the KSP value in Appendix D. Appendix D is the handout that I gave you a minute ago, the chart. In order to write the solubility product constant, the first thing we need to do is come up with the solution equation. So to do that, what we're going to do, we're going to write the compound, CAF2, that was mentioned there. And then I'm going to put S for solid right after it. Then I want to write the solution equation. This will take us back to something we did toward the beginning of the year. This is where you're going to break it up into its ions. If you have a subscript over here, it's going to turn into a coefficient. So we could call this Ca2+.
aqueous plus, this becomes a big 2 of a coefficient, 2F minus aqueous. So that little 2 subscript turns into a coefficient as this dissolves into 1 calcium and 2 fluoride ions. The KSP expression that we would get from this is going to be products where the coefficient turns into an exponent over the reactants, but the reactant's a solid, so we're going to get to leave it out. So for KSP, it'll be Ca2 plus, concentration of calcium ion, times concentration of fluoride ion. What are we going to do with that fluoride concentration? Square it, good. So that coefficient of 2 now turns into an exponent in our equilibrium constant expression. And now the last thing I want us to do is practice using that table. So let's see if we can find calcium fluoride on the table that I passed out. MK, have you found calcium fluoride on the table? What's its KSP value at room temperature? You got it, good job. So we found it on here. This table, again, this is at room temperature, 25 degrees Celsius. So it's about 3.9 times 10 to the negative 11th. Again, all these are insoluble on the table. 10 to the negative 11th is kind of a medium range compared to everything we looked at on the table before. So we practiced writing the equation. We practiced coming up with a KSP. Again, this one was finally a little bit different than the others because this one had something that was squared in it. Now, let's take this another step and look at a problem that is about calcium fluoride. It's on the back of this table that I passed out. We're still looking at calcium fluoride, but we're going to actually use this with an ice chart to actually find a specific value involving the equilibrium constant and the particular concentration. So this is stuff we've actually done a little bit already, but now we're thinking about it in terms of KSP. So we'll still see ice charts, we'll still see solving for X on some of these, or solving for KSP on others. All right, so first up, we're solving for KSP. It says if the molar solubility of calcium fluoride is 1.24 times 10 to the negative third molar at 35 degrees Celsius, what is the KSP at this temperature? We can't just look on the table for the answer this time because it's a new temperature. It's 35 degrees Celsius. To find the KSP when you're given a molarity, you're given a concentration or a molarity, we're going to write the solution process equation. Well, we did that a minute ago. We'll write it again. We're going to write this in terms of X, kind of like a shorthand ice chart. So we'll make a little ice chart, but we'll learn that there's kind of a shortcut to get what you need out of the ice chart. And then we'll write the KSP expression. Finally, we're going to solve for KSP. So I'm going to switch over to notebook paper on here so I can actually write on something. Have a little more room to write on. The first thing we want to do is write that equation again. CaF2, solid actually, yields Ca2 plus 2F minus. That 2 is going to become more important as we go through these things, the 2 in front of the F minus. All right, I like to go ahead and write my KSP just because I can write it right here on the same line. We just figured that out. It's Ca2 plus times F minus, that is, squared. Now, what I want to do now is think about this like we did those ice charts the other day, to think about what's dissolving on this. In a minute, we will put a big X through this side because it's a solid, but I don't want to do that yet because that's where I'm going to get an important number from this. this question said the molar solubility of CaF2 was 1.24 times 10 to the negative third molar. That's how much of this actually did dissolve. So that little bit of it that did dissolve was this much of that. We could think of it as a reactant. It's dissolving. It dissolves. Now there's probably some excess solid that's still in there that didn't dissolve. We could think of those two as zero because they didn't tell me that I already had some calcium or some fluoride dissolved in the solution already. So if I lose those reactants on the left, I'm going to gain the products on the right, same pattern as before. But this is just where it's a little bit different on this one. Because of this 2 right here, what are we going to do for the number that we end up putting in this box in yellow there? Is it going to be the same? Is it going to be 1.24 times 10 to the negative third? It'll be double that, won't it? So maybe 2.48. I'll carry those on down, and then I actually have the amount of each that would be dissolved in the solution. These are my equilibrium concentrations. I don't care about the equilibrium concentration of CaF2. I did need that original number to kind of get started with this. But then I can use that in my KSP expression, and I can solve for KSP. That number needs to be squared over there. Is that 2 showing up on there? I'm squaring that last number. I'm going to come around with some calculators. We can calculate this. It's going to be a small number. Again, it's an KSP or an insoluble salt, so it's going to be small. And also, just based on those numbers, I'm multiplying 2 really small numbers times each other. So I should expect a pretty small number for my answer here. Try to do it on these calculators. I'm going to do that second term first just because it's a little more complicated. So I'll do 2.48 times 10 to the power of negative 3. And then I'll square that number. And then I'll multiply it times 1.24 times 10 to the negative third. The lights are off. My calculator's solar powered. I think I'm getting about 7.63 times 10 to the negative 9. Anybody getting anything very different than that? You want me to look at your calculation method? So at least at 35 degrees, then that's what we would expect the KSP for this to be based on what they gave us there. So that's using the full ice chart, which really shows the full picture of what's happening there. I mentioned it's like a little shorthand ice chart, kind of short way to do these in terms of X that'll save you time. If you're ever just given the molar solubility, that's how much of the actual compound does dissolve, and you're supposed to find the KSP, or if you're supposed to find an individual solubility. There's a shorthand way to solve these KSP problems. It saves you some time. It's a little easier. You start off in a similar way. You can see how they're related here. We're still going to have the calcium fluoride on the left. We're going to write its solution equation. And once you get the pattern down for these, the problems, again, it's kind of just like formulaic. You learn the formula for it. They're pretty quick and easy to solve. What you can do with all of your products over here, if there's one of them, you call it X. If there's two of them, you call it 2X. You would still have the same old idea of your KSP. It's still going to be the things that are soluble over here. Same equation. But now, instead of thinking of this in terms of the full ice chart and keeping up with that 1.24 times 10 to the negative third, we're just calling it X. And then we'll plug in the X when we're ready for it. So then my KSP would look like this. X, because there was only one calcium ion in the products. Fluoride is going to be 2X, because there's twice as many of them because of that big 2 in front of fluoride. And we're still squaring it. That could even be simplified into X times 4X squared. I could simplify it one more time into KSP equals 4X cubed. So again, the 4 and the squared or the cubed stuff, that comes from understanding these numbers and how they're turning into the KSP. So those numbers could be different every time, but now I've actually just got a quick and easy way to solve for KSP. X is going to be the molar solubility of the calcium fluoride. So now I can just plug in the 1.24 times 10 to the negative third for X. I'll do that on the board down here. So anything there's 2 of becomes 2X. If there were 3 of something, it would be 3X. And also, that 2 affected being 2X. And we already know that 2 is important for our squared in our equation here. Good marker. So now I can solve for KSP. 4 times, where X is the molar solubility of that compound, which they told us was 1.24 times 10 to the negative third. And now I'll raise that to the power of 3. 1.24 times 10 to the negative third, my calculator, then I'll say to the third power, multiply that times 4. If I did everything right, I should get the same answer as before, 7.63 times 10 to the negative 9. So both ways work. I like the ice chart giving me all the detail about what's really happening with those relationships in the number. I can see why I'm doing everything with the full ice chart. It's quicker and neater and a lot fewer steps. If I just write that in terms of X, in like a shorthand ice chart, minus X of this, because it dissolved, plus X of that, plus 2X of that, because that was actually what was dissolving. And then X itself, on that little shorthand ice chart, I'll just mention this. I could put minus X there. It's not important for the equilibrium constant expression, but then you can see how that 1.24 is related to what I plugged in for X there. So that technique is also going to be useful for us on this next one, where we're solving for the molar solubility. So we're going to solve a problem now where we go the other way. Before I do that, does anybody have any questions about either of those methods? Because you got really good at the ice charts on Thursday. If you like the ice chart method, just keep using it, because it has everything there. Yes?
We still don't need to provide our answer.
Oh, great question. Yeah, so we're solving for an equilibrium constant. This is a specific one called KSP, but it still is unitless. That's a great question. Unitless, capital K's, I'm going to say always. I can't think of an exception. Capital K's are always going to be unitless for us. All right, let's look at one where we're going the other direction. This one says the KSP for barium, that's called iodate. It's a polyatomic ion. It's good to see what we'll do with the polyatomic ion in the equation. So barium iodate at 25 degrees Celsius is 6 times 10 to the negative 10th. What is the molar solubility of barium iodate? First, we're going to write the solution process equation where some kind of solid is going to dissolve into two aqueous things. Then we're going to write that in terms of x, kind of like we did before underneath the shorthand ice chart, paying attention to any coefficients. And we'll also write an equilibrium constant expression, and then we'll be able to solve it for x to find that molar solubility that we're looking for. Okay, first thing I want us to do, let's break this up into its ions. So we're going to put on the left side barium, BaIO3. So it's just like a nitrate or a phosphate or something. Polyatomic ion. I should say solid. Then we're going to put Ba2+, because that's one of the ions that makes it up. Plus, so this IO3, again, it's a new polyatomic ion for you probably, but how many of these iodates are in the compound? 2. There's 2 of them, so that 2 becomes a coefficient here. 2 iodates, 2 IO3. It's got a 1 minus charge. While we're up here, let's come up with the KSP expression for it. Pavitra, what's my KSP expression here? Good job. Oh, I'm out of room, aren't I? I'll do it down below. All right, nice. I need to plan ahead better. I need to put something underneath right there. I'll put this down low. Okay, finally, I've got that. So now we could do the full-on ice chart, or because this is a KSP problem, I don't have any initial amounts of any of those products or anything, I could just do this in terms of x and go straight from there. So I would lose x of this, I would gain x of Ba2+, and I would gain 2x of IO3 because it's got the big 2 in front of it. So what that's going to allow me to do is go straight into my equilibrium product solubility product constant, and I can say KSP equals x times, this is going to be 2x, that's what was in the place of iodate there, and I still got to square it. This time I know the KSP, they gave me the KSP in the story problem. They said it's 6 times 10 to the negative 10th. And they want me to give my answer in terms of the molar solubility, that is x. So I'm going to distribute that squared to everything in parentheses there. And I'll just simplify this one more time. Now I just have to solve it for x. X is going to be my answer. That's the molar solubility of barium iodate, and this one will have a unit for it. So first I'll divide both sides by 4. And I'll move to the board. I think that's going to be 1.5 times 10 to the negative 10 on the left. Then the last thing I have to do is to take a cube root. I think the easiest way to take a cube root to get rid of that cube is to take both sides to the 1/3 power. Some calculators have a cube root button, but the way I like to do it, if I take both sides to the 1/3 power, so this is what I'm going to put in my calculator here. Times 10 to the negative 10. And I'm going to do raised to the power of, you can do parentheses 0.33333 if you want, but I'll just do 1/3 in parentheses. And that gives me my answer here. So last time we were solving for a KSP, and the answer was it didn't have a unit. This time we're looking for the molar solubility. We're looking for the solubility. So our unit is going to be molar here. What this means is even though barium iodate is considered an insoluble compound, that little tiny bit of it that would dissolve to make a saturated solution of it, most of it would just sink to the bottom. The little bit left over that's still dissolved would have a solubility of 5.3 times 10 to the negative 4. So that's what it means by molar solubility of something. It just means what's its molarity, because these are insoluble compounds, very, very slightly soluble. That little fraction that does dissolve would give that. That's as much as the water can hold at all, which is a real small amount. So don't get too used to the 4x cubed. We saw that on 2 of our examples. Sometimes it'll be as simple as x squared. You know, one of those compounds we were looking at early on was AgBr. And we saw when it dissolved, it was just going to dissolve into 1 silver and 1 bromide. Both of those were aqueous here. Sometimes you'll do minus x on this side and just an x times an x. So sometimes it'll be that the KSP equals x squared. So those 2 examples we looked at both turned into 4x cubed, but that's not always going to be what it is. Sometimes it'll just be 1 times the other. Raise your hand if you have any questions at this point. Sometimes you solve for KSP and you're given the molar solubility. Sometimes you're given the KSP and you solve for X, where X is the molar solubility. All right, the last thing I want us to look at is something we looked at actually when we looked at the chart at the very beginning. What do these KSPs mean when you're comparing them to each other? Well, it's as easy as this. The large value for KSP means that the compound is, I'm going to say very soluble. These are all going to be insoluble, so I just mark that out. The first time I made this, I didn't make it in PowerPoint or Word, so I couldn't change the text here. So I'm going to say it's more soluble. Relatively speaking, it's more soluble. Say a larger value for KSP means it's relatively more soluble in water compared to something else. A smaller value for KSP means the compound is insoluble in water. So you can compare them. They're all considered really insoluble, but among them you can still say which one's more or less soluble. So it's all about comparing these. For things that are totally soluble, they're not going to get KSP values in the first place. So the reason that's useful is so we can answer questions like this last one here. It says, give it some thought. And they say, without doing a calculation, so none of this stuff, let's look at these. Which will have the greatest molar solubility in water? AgCl, where it's 1.8 times 10 to the negative 10. AgBr, 5 times 10 to the negative 13. Or AgI with a KSP of 8.3 times 10 to the negative 17th. Of all three of those, which one's going to be the most soluble in water? Vivi, what do you think? Just this last one that says give it some thought. I want to know which of those three compounds has the greatest molar solubility in water. AgCl, you got it, because even though all those are small numbers, the biggest of those small numbers is 10 to the negative 10th. So we have to go with the AgCl. You got it. All right, let's take a little